morning everyone. Myself Sreevani, working as an assistant professor in the Department of ECE in Institute of Aeronautical Engineering, Dundigal. So in the today's lecture, we'll learn different types of capacitors. Under this, the second and third type of capacitors are called cylindrical type capacitor and spherical type capacitors. Based upon this, the capacitance is to be derived. Then from that, we are going to estimate the resistance which is associated with that. Then from that, time constant of the circuits can be calculated. So firstly, the second type of capacitor called cylindrical type capacitor. Now, before going to discuss about this cylindrical capacitor, so what do you mean by capacitance? Then based upon that, what is the general equation for that capacitance? Now, based upon that, how we are going to calculate the capacitance? So, in general, the capacitance C can be given by, is the ratio of Q by V. C equal to Q by V, where Q is said to be charge of one of the plates of the capacitor and V be the potential difference between two plates. Now, in order to calculate the capacitance of whatever may be the type of the capacitor, whether it is parallel plate capacitor or cylindrical type capacitor or spherical type capacitor, we need to consider the fundamental equation for that is C equal to Q by V. Now from that, how much charges exist in that we'll calculate. Then potential difference between the two plates we need to calculate. Then finally, we have to substitute Q and V in this, the capacitance equation. And before going to derive the equation for this, we need to remind what is the relation between electric potential V and the field intensity E is given by minus integral L E dot dl, where E is said to be electric field intensity and dl be the displacement length in the particular direction. Now, here the second type of the capacitor we have considered is here cylindrical type capacitor. Means whatever may be the capacitor, but it has two plates which carries, the plate 1 carries positive charge and plate 2 carries negative charge. And each is having charges, means their magnitudes are the same and the directions in which they are considered is to be differ. So here, first consider here the simple figure which is representing cylindrical type capacitor, and it is in general we consider as coaxial cable or coaxial cylindrical capacitor. So a coaxial capacitor is nothing but essentially it is a coaxial cable or simply coaxial cylindrical capacitor. So if you consider that this is the outer conductor and outer plate, and inside that we have inner conductor, nothing but inner plate, plate 1, and plate 1 carries a positive charge as plus Q and plate 2 carries negative charge as minus Q. So here 1 and 2 are representing respectively plates which carries plus Q and minus Q respectively. And these two charges are differed by a small distance, and which is represented by here dielectric constant epsilon. Or sometimes it might be free space medium also. Now, if you consider the inner figure, means it is drawn with the radius as A and outer conductor which is having the radius as B. If you observe, the relation between these two is given by here B is greater than A. Right? So this is the outer conductor or plate 2 which carries negative charge and inner conductor or plate 1 which carries positive charge. So the coaxial capacitor is nothing but here considered coaxial cable or coaxial cylindrical capacitor. So it is simply, if you observe, an example for coaxial cable is a dish wire which we have considered in this case. So inside outer one there is a exist one which is represented with black coated wire, and inside there is a white coated wire is there. Then inside there is a copper wire which carries current. So it is an example for a coaxial cable, and if you observe here, this is the example for that. So now a length of the coaxial cable is given by L, and this is cylindrical type, means we need to consider the variables L related to the cylindrical coordinate system, and those are given by rho, phi, z are the three coordinate system variables for the cylindrical coordinate system. Now for this, differential components of the cylindrical coordinate system means d rho, d phi and dz. So why we have considered here the phi component as along with the radius as rho d phi means this is the one which is representing with length of an arc shape. So if you find the area angle is here phi, then length means then this is represented with along with the formula L equal to r theta, where r is the radius of that particular shape and theta be the angle which we are going to measure. So depending upon this formula, this phi component is given by rho into d phi, right? So now consider the length L of two coaxial conductors of inner radius A and outer radius B. Now if you observe from this figure, it is represented with B is greater than A, means outer plate radius is greater than that of the inner plate radius. Now let the space between the conductors and it is filled with a homogeneous dielectric with a permittivity as epsilon. Now to derive the equation for that cylindrical capacitor capacitance, now we have considered, we assume that the conductors 1 and 2 respectively carry plus q and minus q uniformly distributed on them. So in the figure, plates 1 and 2 respectively carries plus q and minus q, and those two charges are uniformly distributed on them. If the charge is uniformly distributed, we need to consider Gauss law. So that's why by applying Gauss law to an arbitrary Gaussian cylindrical surface of radius rho. So arbitrary means we have to define its own length, our own defining length or our own defining surface area. So by applying Gauss law to an arbitrary Gaussian cylindrical surface of radius rho, which is ranging from here, A is less than, rho is less than B. So inner conductor radius as given by conductor 1 which carries plus q and the outer conductor radius which is given by B and that is carries minus q. So it is represented with plate 2. Now the radius is ranging from here, A is less than, rho is less than B. Now according to Gauss law, so we know that according to Gauss law, psi equal to q enclosed. Now what do you mean by psi here? Means psi is defined as here flux passing through any closed surface. Hence, passing through any closed surface means it occupying some area, then that area is considered to be is here along with the flux density and it is denoted with d bar into ds. So psi equal to closed surface integral is d dot ds. And q enclosed, charge enclosed by that region, cylindrical region is given by q enclosed is nothing but q only here. Hence, q enclosed equal to q. Then first find the psi. So closed surface integral is d dot ds. Now, if you want to evaluate this one, the flux density due to which direction means rho direction. Why we have considered here rho direction means the inner and outer plates are having the radiuses with the respectively A and B. Hence, the direction we need to consider is here A rho. Hence, we have to remember first the formula for this differential surface area in cylindrical coordinate systems. So, before going to write the formula for this differential surface area in cylindrical coordinate system, we need to revise what are the coordinate variables. Rho, phi, z are the coordinate system variables and the differential components are d rho, rho d phi and dz are the three differential components in cylindrical coordinate system. Now, phi rho direction we have to consider. Rho direction means this is the direction we need to consider d rho into a rho d phi into a phi and dz into az. So now rho direction we need to consider means then we have to multiply these are the two to get the surface area. Hence, rho d phi dz into a rho is the formula for the ds. Now we know that d can be expressed as here epsilon into e. Now in place of d, if we substitute epsilon into e, then epsilon might be the constant, then closed surface integral is e dot ds. And this e is evaluated with respect to the rho, hence this can be written as e rho. Now this e rho into a rho can be considered for the d, and if you evaluate this closed line in surface integral is ds, then that can be obtained as here epsilon q equal to epsilon integral s e dot ds can be written as epsilon into integral s. S means surface integral. We have to consider for 2 times as the integration. Then E can be given by E rho A rho dot ds. Formula is rho d phi dz into A rho. Now E rho and epsilon might be constant and rho is also a constant. Why rho is a constant means your differential variables are phi and z, hence rho can be considered as a constant. Now E rho epsilon into rho, then surface integral means this 2 times we need to integrate and variables are phi equal to 0 to 2 pi and this z is the given by z is equal to 0 to L. Why? Because initially from the figure we have considered length of the cylinder is given by L. So Z is the variable which is ranging from 0 to L and by default we know that phi which is ranging from 0 to 2 pi, then d phi dz and A rho dot A rho is equal to 1. Why? Because we know that the dot product representation of two same unit vectors result is 1. Not only arrow dot arrow, but is az dot az is also 1, then a phi dot a phi is also 1. So from this we can see that dot product or dot product representation of two same unit vectors result is 1. Now according to this, here arrow dot arrow is 1, then d phi dz is left out. Now epsilon rho e rho into integral. If you integrate this one, phi is the result, then substitute limits as 0 to pi. Then if you're going to integrate this one, z is the variable, then substitute limits as 0 to L. Now if you substitute phi by 2 pi, z by L, then 2 pi epsilon rho L E rho is the value of Q. Now from this, estimate the value of E rho, or simply E can be written as Q by 2 pi epsilon rho L. Okay, into A rho. So from this we have got the equation for E as Q by epsilon 2 pi rho L into A rho. Right? Now after finding this E, then we need to find from that E electric potential as V. And we know that the relation between V and E is given by minus integral L E dot dl. And length LB is between the cylinder radius and which is from A to B. So by neglecting flux fringing effect on the cylinder ends, then V can be given by minus integral 1 to 2 E dot dl, which is equal to minus integral A to B Q by means E value we have calculated just now, that is E equal to Q by 2 pi epsilon rho L, then into A rho. Then that value we need to substitute here in place of E. Then Q by 2 pi epsilon rho L A rho dot dl value is nothing but d rho into A rho. Why d rho into A rho means we have considered only one direction component. Length means we need to consider only one particular direction. Hence dl is nothing but d rho into A rho. Hence from this, if you multiply these two, A rho dot A rho value is 1. Why? Because dot product representation of two same unit vectors result is 1. Now according to that, A rho dot A rho equal to 1. Then Q by 2 pi epsilon L is a constant. Then minus integral A to B. Then minus Q by 2 pi epsilon L is a constant. 1 by rho into d rho is left out. Now minus Q by 2 pi epsilon L, then 1 by rho integration is ln of rho, then substitute limits as A to B in this, which is equal to minus Q by 2 pi epsilon L into ln of A minus ln of B. Now if you multiply this negative with this term, then Q by 2 pi epsilon L ln of B minus ln of A. So we know that the formula ln of log B minus log A can be written as log of B by A. Now from that, Q by 2 pi epsilon L ln of B by A is the value of electric potential which is to be obtained in the case of cylindrical capacitor. So from that we have got V equal to Q by 2 pi epsilon L ln of P by A. Now the capacitance of the coaxial cylinder is given by according to the fundamental definition of a capacitance, that is C equal to Q by V. Now if we substitute Q by and V by this equation, hence the C equal to Q by V and Q by, if we substitute V by this equation, means Q by 2 pi epsilon L ln of V by A. Now numerator Q and denominator Q gets cancelled and C equal to 2 pi epsilon L by ln of V by A is to be obtained in the case of the capacitance of cylindrical capacitor. So, capacitance of a cylindrical capacitor is given by C equal to 2 pi epsilon L by ln of B by A, where epsilon is permittivity of the material and L be the length of the coaxial cable and ln of B by A, where B is said to be outer plate radius and A is inner plate radius. Right? So, the capacitance of the cylindrical capacitor is to be obtained as 2 pi epsilon L by ln of B by A. Now, third type of the capacitance which we have considered in the case of electric fields is spherical capacitor. So, depending upon the shape we have considered, depending upon that we need to consider respective coordinate system variables. So, spherical capacitor means spherical coordinate system variables we have to consider, and three variables are given by r, theta, phi. Right? So, r is the radius, theta and phi are the two angles which is to be measured with respect to the latitude and longitude of the earth. And a spherical capacitor is the case of two concentric spherical conductors, and here also inner plate is having the total charge which is uniformly distributed on them is on here is plus q, and it is drawn with a radius as a, and outer plate is drawn with a radius b, and outer plate is fully charged with negative charge, that is minus q, means plus q and minus q uniformly distributed on plate 1 and 2 respectively. So consider first of all a spherical capacitor, and here is the case of two concentric spherical capacitors or conductors, and consider the inner sphere of a radius a and the outer sphere of radius b, and the relation between b and a is given by here b is greater than a, and it is separated by a dielectric medium with permittivity as epsilon. So that's why every time we will particularly consider the two plates are separated by a small distance or a variable or a medium called dielectric medium. Sometimes it might be free space medium is also. Right? So now, based upon this, if the charges are uniformly distributed on the respective plates as 1 and 2, means we assume that plus q and minus q on the inner and outer spheres respectively. By applying Gauss law means if the charges are uniformly distributed in the plates 1 and 2 respectively, hence we need to apply Gauss law. Means if the symmetrical charges exist, then we need to apply Gauss law. So by applying Gauss law to an arbitrary Gaussian spherical surface. Previously we have considered arbitrary cylindrical Gaussian surface. Why? Because there we have considered cylindrical type capacitor. Now it is spherical capacitor. So by applying Gauss law to an arbitrary Gaussian spherical surface of radius r. So spheres we need to draw with the radius as r, and this radius is ranging from a to b, and the condition here we have considered is a is less than or is less than b. Previously for a cylindrical type we have considered over there is a is less than rho is less than b. Rho is the radius of that cylindrical cable, hence rho notation. Now r is the radius of these two spheres, hence the range of this is given by a is less than r is less than b. So according to this, so spherical capacitors means we have to consider the variables as r, theta, phi, or the spherical coordinate system or polar coordinate system. So along with this we need to consider differential components also. So those differential components are dr, r d theta, and r sin theta d phi. So r d theta, r sin theta d phi. generally it is rho d phi, and rho is expressed in terms of means if you consider the transformation between cylindrical to spherical, then rho can be given by here, rho can be given by r sine theta. Hence, in place of rho, we just consider r sine theta into d phi. So these are the three differential components which we have considered in the case of spherical coordinate system. Now the direction is given by here. R direction means the first component is unit vector component is AR, and second is A theta, and third one is A phi. So if the direction is to be related to AR means we need to multiply rest of the two to get differential surface area in the spherical capacitor. Hence ds is equal to, already r is there in the formula itself, r into r becomes r square sine theta d theta d phi into AR is the formula for the differential surface area, right? So now we're going to evaluate that one with respect to this ds, means according to the Gauss law, we know that psi equal to q enclosed. So this q we are going to estimate now here, flux passing through closed surface area we need to calculate. Why? Because spherical region or cylindrical region means it must be a closed region. That's why closed surface integral S d dot ds is to be evaluated. Now if we substitute d by epsilon into E, then d equal to epsilon into E, then if you consider epsilon as a constant, then epsilon we might be written here out of this integration, then closed surface integral S E dot ds, right? Now q can be given by q equal to epsilon integral S E, means ER AR dot ds, means r square sine theta d theta d phi AR, right? Why ER means the electric field intensity E we have considered with respect to the radius of R here, along with the component is given by ER into AR. So previously we have considered that is E is nothing but E rho into A rho. Why? Because there we have considered this shape as cylindrical capacitor. Now is related to spherical, hence that radius is given by with respect to the variable called R, hence E is replaced by ER into AR. Then epsilon into ER, and AR dot AR value is 1. Why? Because as we know that the dot product representation of a same unit vectors result is 1, hence AR dot AR equal to 1. Then epsilon ER surface integral means we have to consider the two differential variables as with respect to the theta and phi. Why? Because surface we have considered, hence two direction integration components we need to consider. Hence epsilon ER into R square is also a constant. Then theta equal to 0 to pi and phi equal to 0 to 2 pi sine theta d theta d phi is obtained. So epsilon R square into ER integral, first 0 theta equal to 0 to pi sine theta d theta, then phi equal to 0 to 2 pi d phi can be obtained. Now epsilon R square into ER, then if you integrate the sine theta, then minus cos theta is to be obtained, then substitute limits as 0 to pi, and here if you substitute integrate this one, phi is the resultant one, then if you substitute limits as 0 to pi, 0 to 2 pi, then epsilon R square ER into minus cos pi, then minus of minus plus cos 0 into 2 pi is to be obtained, then which is equal to 2 pi epsilon R square into ER, then minus cos pi. So cos pi value is minus 1, then already minus is there, minus of minus becomes 1, then 1 plus cos 0 value is 1, then it becomes 4, 2, 1 plus 1 is 2, 2 into 2 becomes 4, 4 pi R square epsilon into ER is the value of Q. Now from this you are going to estimate ER equal to Q by 4 pi R square, 4 pi Q by 4 pi R square into epsilon can be obtained. So ER. So or in general E can be written by Q by 4 pi epsilon r square into AR. This is the value of E is to be obtained in the case of spherical capacitor. Right? Now, the potential difference between the two conductors. Now, to calculate from the electric field intensity, electric potential as we know that V equal to minus integral L E dot dl. Right? So now if we substitute in place of E by that formula means Q by 4 pi epsilon r square into AR here, and dl is equal to dr into AR. Why? Because E is evaluated with respect to R, hence dl is also considered with respect to the R, hence the formula for dl becomes dr into AR. Hence V equal to minus integral 1 to 2 E means Q by 4 pi epsilon r square into AR dot dr into AR. And Q by 4 pi epsilon is a constant, then minus integral 1 to 2. 1 is the variable, 1 is the plate 1 which is located at A, radius is A, and B is at 2 is at B, then 1 by r square into dr is left out. Right? So minus Q by 4 pi epsilon into 1 by r square dr. So minus Q by 4 pi epsilon, then 1 by r square formula becomes minus 1 by r. Then if you substitute limits as a to b. Why? Because integral x power n formula is x power n plus 1 by x power n into dx. Then formula is x power n plus 1 by n plus 1. So here we have r power minus 2 means 1 by r square can be written as r power minus 2. Then integral r power minus 2 into dr can be written as r power minus 2 plus 1 by minus 2 plus 1. Then r power minus 2 plus 1 is r power minus 1 by minus 1. Then it becomes minus 1 by r. So now 1 by r square if you integrate, then the resultant will be minus 1 by r. Now already formula itself negative is there, minus into minus becomes plus, then Q by 4 pi epsilon. Then if you substitute R by limits as A and B, then 1 by A minus 1 by B is the value which is to be obtained in the case of electric potential. Hence, V is to be obtained as here Q by 4 pi epsilon into 1 by A minus 1 by B. Now, the capacitance of the spherical capacitor is given by, in general, the capacitance C can be defined as it is the ratio of the charge of one of the plates of the capacitor to the potential difference between the two plates, and C equal to Q by V, which is equal to, now if we substitute here, C equal to Q by V. Now Q by, the value which we have got for V is Q by 4 pi epsilon into 1 by A minus 1 by B. Right? So this Q and this Q gets cancelled, which is equal to 4 pi epsilon by 1 by A minus 1 by B is obtained the value of the capacitance which is related to spherical capacitor. Right? So that is obtained as here C equal to Q by V, which is equal to 4 pi epsilon by 1 minus A minus 1 by B. Suppose inner conductor radius as A and outer conductor radius as B, means A and B are respectively plate 1 and 2 charge radius. Right? So here let B tends to infinity, means outer conductor radius to be assumed as infinite. Next, if we substitute here, if B tends to infinity, if we substitute here in this equation, then 4 pi epsilon by 1 by A minus 1 by infinity. So minus 1 by infinity, something by infinity becomes 0, hence 4 pi epsilon by 1 by A, which is equal to 4 pi epsilon into A is the spherical capacitor of the capacitance which is to be considered. Their outer conductor radius is tending to infinite in region. So, which is the capacitance of a spherical capacitor whose outer plate is infinitely large. If you are assuming whose infinite secondary means outer plate radius is, outer place capacitance is, plate is infinitely large, then the capacitance is to be obtained as here C equal to 4 pi epsilon A, or if you are considering for a finite value B, then the capacitance of the spherical capacitor is calculated as C equal to Q by V, which is equal to 4 pi epsilon by 1 by A minus 1 by P, where epsilon is the permittivity or dielectric material which is separating between plate 1 and 2, right? And A is the radius of the inner conductor and B is the radius of the outer conductor. So this is the way we have calculated three types of the capacitors, capacitances. That is, first case if we consider it as parallel plate capacitor, and the second case cylindrical capacitor, and the third one is spherical capacitor. So based upon this, we are going to estimate what is the resistance which is associated with the three types of the capacitors, right? So before going to calculate, we need to know what is the relation between if two resistors are connected in series and if two capacitors are connected in parallel. If two capacitors are connected in series, C1 and C2, the connection between two, if you observe here, these two are connected in series, and if you observe, C1 and C2 are connected in parallel. So how will you differentiate if two are connected in series and if two are in parallel? Means if only one component is between the two elements, then those two are said to be series. If both the ends are starting edge and ending edges are same, then two are said to be or connected in parallel, right? So if two capacitors with a capacitance C1 and C2 are in parallel, then the total capacitance C can be considered as here directed addition we need to consider, and C equal to C1 plus C2. And if two capacitors are connected in series, then the total resistance capacitance is obtained as here. Means if two capacitances are connected in series, their reciprocals are going to add. Hence 1 by C equal to 1 by C1 plus 1 by C2. Then C equivalent can be obtained as here C1 C2 by C1 plus C2, right? So based upon this, now as we know that resistance R is given by, according to Ohm's law, V equal to IR. Now from this, R can be obtained as V by I, and we know that the relation between here V and I. So V is expressed in terms of electric fields, means the relation between E and V is given by V equal to minus integral L E dot dl, and I can be given by I means current, and it is related to the conduction current density. Hence I equal to integral S J dot ds, where J is said to be conduction current density and it is given by sigma into E. So sigma, then close the surface integral S E dot ds is the value of this I. Now if we substitute this V value and I value here, now R equal to V by I, then it becomes minus integral L E dot dl by closed surface integral S sigma into E dot ds. Where sigma into E is given by collectively, that is conduction current density, and it is J, right? So R equal to V by I, then integral minus integral L E dot dl by closed surface integral S sigma E dot ds, right? So this is the value which we have got from the electric field's resistance. Similarly, the capacitance C can be given by in terms of electric fields, and C equal to Q by V. Then the charge Q is to be obtained here. Q equal to Q in terms of electric fields. Then close the surface integral S D dot ds. So this is to be obtained from the Gauss law. Then psi equal to Q enclosed. So Q is nothing but psi. So that psi is given by flux passing through any closed surface. Hence close the surface integral S D dot ds, right? So if we substitute d by epsilon into E, then Q becomes epsilon integral S E dot ds. And similarly for V, we know that minus integral L E dot dl, right? So if we substitute Q by V here, then epsilon close surface integral S E dot ds and minus integral L E dot dl is the formula for the V. Hence, if we multiply R and C here, we multiply R and C. So R is the value which is obtained from this minus integral L E dot dl by sigma closed surface integral S E dot ds into C is to be obtained as epsilon closed surface integral S E dot ds by minus integral L E dot dl. right? So in the numerator, integral L E dot dl, and in the denominator, integral L E dot dl gets cancelled, and closed surface integral S E dot ds, and this S E dot ds gets cancelled. Hence, RC equal to epsilon by sigma is to be obtained. So already we have learned that TR is nothing but relaxation time or rearrangement time for the electric fields is given by RC equal to epsilon by sigma. So from these two relations, we have got RC equal to epsilon by sigma. So this is called relaxation time or rearrangement time for the electric fields. Now based upon this, all the capacitances, we are going to calculate resistance is related to the respective three types of the capacitors, right? So now for a parallel plate capacitors, first we have got here for a parallel plate capacitor, in general we need to know C equal to Q by V, which is equal to epsilon S by T is obtained. Epsilon is the permittivity or dielectric constant which is separated between two parallel plates, and S be the plate area and D be the distance between the two plates. So epsilon S by D is the value for the parallel plate capacitor, and R can be obtained as like this. Means RC equal to epsilon by sigma. Then from this we are going to calculate R equal to means epsilon by sigma into C. Now epsilon by sigma into C value, if we substitute epsilon S by D, then epsilon gets cancelled, then D by sigma into S is the resistance which is associated with the parallel plate capacitor. D is the distance between the two plates, and sigma be the conductivity of that, and the resistance S be the surface area. Okay, so this is the way we have calculated resistance of the parallel plate capacitor. Similarly, the second one is for a cylindrical capacitor. Means again we have got here C equal to Q by V, and it is given by 2 pi epsilon L by ln of B by A for the cylindrical capacitor. And we know that the resistance and capacitance RC is given by epsilon by sigma. Then from this, R equal to epsilon by sigma into C. Then epsilon by sigma into C value here 2 pi epsilon L by ln of B by A. So epsilon gets cancelled. Then ln of B by A by 2 pi sigma L is the value of R for the cylindrical capacitor. Okay. So for a cylindrical capacitor, C is to be obtained as 2 pi epsilon L by ln of B by A, and from that R value is ln of B by A by 2 pi sigma into L. So if you observe, R is the resistance and sigma be the conductance or conductivity. So we know that the relation between two are reciprocal to each other. So in each case means for a parallel plate capacitor, for a cylindrical capacitor, or for a spherical capacitor, there should be the relation is inversely proportional to each other. Now for the third case we have considered is here for a spherical capacitor. So for a spherical capacitor means C equal to Q by V again. So C value which we have got from the analysis is 4 pi epsilon by 1 by A minus 1 by B. So again we know that RC equal to epsilon by sigma. Then from this R equal to epsilon by sigma into C, then epsilon by sigma into a substitute C by 4 pi epsilon by 1 by A minus 1 by B, right? So epsilon gets cancelled, which is equal to 1 by A minus 1 by B by 4 pi sigma. Here also if you observe the relation R and sigma, two are reciprocal to each other, right? So for a spherical capacitor, C value is to be obtained as 4 pi epsilon by 1 by A minus 1 by B. Then R becomes 1 by A minus 1 by B by 4 pi sigma. Okay. Then for an isolated spherical conductor. So isolated spherical conductor means this is the case, the outer conductor radius B is tending to infinite in this particular case. If B tends to infinity, then C becomes, from this equation, C equal to 4 pi epsilon by 1 by A minus 1 by B, means B tends to infinity. If we substitute B by infinity in this equation, Then we have got 4 pi epsilon by 1 by a minus something by infinity becomes 0. Then from this 4 pi epsilon into a is the value which we have got in the case of a spherical capacitor, right? 4 pi epsilon a. Now after that, from this R is going to calculate. So to calculate that R, we need to consider again the time constant or relaxation time, that is RC, which is equal to epsilon by sigma. Now epsilon by sigma into, from this R equal to epsilon by sigma into C, then epsilon by sigma into, we substitute C by this value 4 pi epsilon into A, and this epsilon gets cancelled, then R equal to 1 by 4 pi sigma into A. So here also this R and sigma are need to be inversely proportional. So R equal to 1 by 4 pi sigma into A. So for an isolated spherical conductor means, if you are assuming the outer sphere, means example we have considered for that here as Earth should be an isolated. Earth is an example for outer conductor. Hence, that C can be obtained as here 4 pi epsilon into A, and R is to be obtained R equal to 1 by 4 pi sigma into A. So, this is the way we have calculated three types of the capacitors. As for the parallel plate capacitor, C is to be obtained as epsilon S by D and R equal to D by sigma into S. And the next one is for a cylindrical capacitor, C is 2 pi epsilon L by ln of B by A, and R is to be obtained as ln of B by A by 2 pi sigma into L. And for a spherical capacitor, C is given by 4 pi epsilon by 1 by A minus 1 by B, and R is 1 by A minus 1 by B by 4 pi sigma. And for an isolated spherical conductor means, if we are assuming B tends to infinity, outer conductor radius should be ideally or infinitely large. Then B tends to infinity case, then C becomes 4 pi epsilon into A, and R value which is to be obtained as R equal to 1 by 4 pi sigma into A. Right? So this is the way we have calculated three types of the capacitors which are associated in the electrostatic fields. So based upon that, firstly we need to know capacitance equation C equal to Q by V, and the relation between E and V is given by V equal to minus integral L E dot dl. Now according to that, Gauss law we need to use. Why? Because in three cases, for a parallel plate case or cylindrical or spherical type, whatever the type of the capacitor we have considered, we need to use the Gauss law. Why Gauss law means, the type of the capacitor we have considered means in each case two plates are to be considered. In each plate the charge is to be uniformly distributed in the respective plate. Hence, if the charge distribution is uniform in that particular case, we need to use Gauss law. Hence, that Gauss law is to be obtained as here Q enclosed is equal to psi, and that should be closed surface integral S d dot ds. Now from this we are going to calculate the value of E. Then this E value should be substituted in place of V to get the potential. Then from that V is to be substituted in the case of the capacitance C to get the type of the capacitance respectively for a parallel plate and cylindrical and spherical type. And the third case also we have analyzed, means if the outer conductor radius is to be infinitely large, that is the case also. We have evaluated the capacitance C is given by 4 pi epsilon A, and R is to be obtained from the relaxation time, that is 1 by 4 pi sigma into A. So whatever may be the type of the capacitor we have considered, or for all the resistors which are associated with the parallel plate or cylindrical type or spherical type of the capacitors, R and sigma are inversely proportional to each other. As we know that resistance R and the conductance G are reciprocal to each other. Like this, R equal to 1 by G or G equal to 1 by R, the relation is to be obtained as here R is inversely proportional to the 1 by sigma. Right? So, thank you.
Like, share and subscribe. Hit the bell icon for more updates.